Indices and Logarithms. A number x is said to be in index form if we can write it as some number raised to the power n, where of course y is called the base, n the index or power or exponent. So we say y to the index of n, or y raised to the power n, or y to the exponent of n. What I shall use throughout this video, or mostly, shall be y raised to the power n. So if any number x can be expressed as some number raised to a particular power, of course, where n can be any number, negative, positive, fraction, whatever it is, then this number x is said to now be in the form called index form. Now, when we have more than one of these index forms, we now have indices. For example, if I write 2 raised to the power 2, this number is in this form, y raised to the power n, where y is 2 and n is also 2. So the 2 down here is called the base, and the 2 up here is called the power, index, or exponent. Now, what this simply means is that the base should be multiplied 2 times. Just like in this case, this means that the base y should be multiplied n times. Now, the base is 2 and the power is 2. So this simply means 2 times 2. We should multiply the base, the number of times of the power. Now, 2 times 2 is nothing but 4. What this means is that the number 4 has been written in a form that has a base and some power. So in index form, we have written 4 as 2 raised to the power 2. So 4 is equal to 2 raised to the power 2. So this is the index form of the number 4. Another example, if we have 2 raised to the power 3, and this means we should multiply the base how many times? 3 times. So that means 2 times 2 times 2. And that gives us 2 times 2 is 4, 4 times 2 is 8. So in index form, the number 8 can be written as 2 raised to the power 3. I should point out at this point that 2 raised to the power 3 does not mean 2 times 3. It doesn't mean 2 times the power, no. It means that the number, the base, should be multiplied the number of times of the power. And finally, if we have 5 raised to the power 2, this would mean 5 times 5. The base is 5, the power is 2. We multiply the base 2 times. So 5 times 5 is 25. Therefore, 25 in index form is nothing but what? 5 raised to the power 2. So, the next one to look at are laws of indices. Since there are certain laws, that govern the operations of indices, it is good that we know most of these laws, if not all of them. Laws of indices. L1 stands for law 1, and we call this law the multiplication law. This law states that if we have an index form, x raised to the power a, for example, multiplied by another index form, x raised to the power b, this law says that if the bases are the same, x raised to the power a has base a, x raised to the power b has base b, you observe that these two index forms have a common base, the same base. What this law is saying is that if the bases are the same and we are multiplying the two index forms, we should just take out one of the bases, which is x, and sum up the powers. So the power of the first index form is a, power of the second index form is b. We now add a plus b. We call this the multiplication law of indices. For example, if we have x raised to the power 2 times x raised to the power negative 3, we can apply the first law of indices here, the multiplication law, because the first index form has x as its base, the second index form has x also as its base, and between them we are multiplying. That's all we need to see. Since this happens by this law of indices, we can take out the base x, and the first power there is 2, the second power is minus 3, and then we add them up. So that becomes 2 plus minus 3, and that is nothing but x raised to the power 2 plus times minus is minus 3, and that gives us x raised to the power 2 minus 3 is minus 1. That's the first law of indices. The second law of indices, which we shall call division law, sometimes it's called the quotient law. states as follows. That if we have two index forms, x raised to the power a, for example, and x raised to the power b, and if between these two index forms we have the division sign, what we should write is this. The first index form has base x, second index form has also the same base. This law says that if between them we are dividing, we should just take out the base and then subtract the exponents. So the first power here is a, the second power is b. The law says you should do a minus b. So x raised to the power a divided by x raised to the power b is equal to x raised to the power a minus b. This law can also be stated as follows. We can write it like this. We can also write x raised to the power a divided by x raised to the power b. It means the same thing. This is equal to, the bases are the same. We take the base and then subtract the exponent. So the exponent up, or the power up, is a minus the power down is what? B. So the two laws, the two expressions mean one and the same thing. For example, if we have, say, 3 raised to the power 3 divided by, say, 3 raised to the power 2, I want to apply the second law of indices here. This is simple because the first index form has base 3, the second index form has base 3, so the base is common. We just take out one base, 3. The power of the first index form is 3, second index form is 2. We now do 3 minus 2. So that 3 minus 2 is 1. And 3 to the power 1 means 3 times 1. And that is equal to what? 3. So that is the second law of indices. Law number 3 of indices, which we shall call the power law, states the following. That if we have an index form x raised to the power a, for instance, and this index form has another power outside, say b. So here we have an index form x raised to the power a, that is the full index form, has base a and power of b. And that index form completely is raised to another power b. So we observe here that there are two powers. There's a power inside, there's another power outside. Hence the power law. So what the power law of indices states is that once we have two powers like this, one inside and the other one outside, the law says that we should multiply out the powers. So this would mean x raised to the power, the first power is a, times the second power outside is b. So that a times b becomes x raised to the power what? ab. For instance, if you have, say, x raised to the power, let's say 2 raised to the power 3 and a raised to the power 2. What do you observe here? You observe that in the bracket there's an index form with the base and power, and that index form is raised to another power outside the bracket. So what this law is saying is that we should multiply out the two powers we find. The first power is 3, second power is 2. So this will now be 2 raised to the power 3 times the power outside 2. That becomes 2 raised to the power 3 times 2 is 6. And this means we should multiply 2 how many times? 6 times. 2 times 2 times 2 up to 6 times. So that is the power law of indices. The next law that follows very quickly is the zero power law, which states that any base raised to the power 0 is simply 1. Very simple. That if you have any index form whose power is 0, that index form amounts to 1. For example, if you have 10 raised to the power 0, the answer is just what? 1. If you have 100 raised to the power 0, the answer is 1. Whatever you have, a million, whatever it is, raised to the power 0, the answer is what? 1. And we call this the zero power law. Law number 5, we shall call the negative power law. It states that x raised to the power minus a. Here, the power is now a negative, number. It could be minus 1, minus 3, minus half, whatever it is. But the power is certainly negative. So once we have a negative power, what we simply write is this. We simply write 1 all over x raised to the power a. Negative power law. Of course, there's a condition, provided that x here is not equal to 0. Because if x is equal to 0, then the whole of this will not be defined. So if you have a negative power, on your base, you simply write 1 divided by that base to the power without the minus sign. So this means this, and of course this also means this. For instance, if we have 2 raised to the power minus 3, here the base is 2 and the power is minus 3, which is negative. So we'll now apply the negative power law here. By this law, we can write this as 1 divided by 2 raised to the power 3, which is equal to 1 divided by 2 to the power 3 means 2 times 2 times 2. And that is 1 all over what? 8. Another example, if we have 2 raised to the power minus 1, this will become, here also the power is negative 1. So by this law, we simply write 1 divided by 2 raised to the power 1. But 2 raised to the power 1 is 2. So this is nothing but 1 all over 2. So we've applied the negative power law. Law number 6 is what we call the fractional power or root law. This law states that if we have x raised to the power, say a over b, we observe here that here the base is x, but the power is a fraction, a over b, where the numerator is a and the denominator is b. That if we have an index form with a fractional power, what we should write is this. The denominator is b, so we write the bit root. This is how I write it. What should be here must be the denominator. The bit root of the base, which is x, all of it raised to the power of a, the numerator raised to the power a. We can also write this sometimes as the bit root of x raised to the power a, and the a will be inside. These two forms are, as a matter of fact, equivalent, are the same. So the law is saying that if you have a fractional power, of course a fraction will have two parts, a numerator and a denominator. That what you should now write is the denominator is what you put on the root sign. So that becomes the bit root of the base x raised to the power a. This is what we commonly use. But note that we can also express this as this. For instance, if we have 8 raised to the power 2 over 3, this is clearly the case of fractional power or the root law. Because here 8 is the base and the power is 2 over 3, and that's a fraction. So the fraction here has 2 as its numerator and 3 as its denominator. So according to the fractional power or root law, we can write this as what? The denominator is 3. So the cube root of the base, which is 8, raised to the power of 2. That becomes, and the cube root of 8 simply means the number that can be multiplied 3 times to get 8. So we know that 2 times 2 times 2 3 times is 8. Since 2 times 2 is 4, 4 times 2 is 8. Since 2 can be multiplied thrice to give us 8, it means that the cube root of 8 is 2. So the cube root of 8 is 2 raised to the power 2. And 2 squared simply means 2 times 2, which is what? 4. So 8 raised to the power 2 over 3 is nothing but 4. If we want, let's use this other form for it. Now in this other form, this would mean the cube root of 8 raised to the power a. Our a here is 2 raised to the power 2 inside. And that will give us the cube root of 8 squared is 64. And 64, the cube root of 64 simply means what number can be multiplied 3 times to get 64? Can multiply itself 3 times to get 64. The number here is 4. Since 4 times 4 times 4. 4 times 4 is 16. And 16 times 4 is what? 64. So the cube root of 64 is equal to 4. So you've seen that the answer we have here in this form and this other form are just the same. So we take note of this, the fractional power law. However, this law has a special case. Now, if the denominator of our fraction is 2, let's say x raised to the power 1 over 2, then we shall write this as the square root of x raised to the power 1, which is the same thing as what? The square root of x. What are we trying to say here? You observe here that though the denominator is 2, we have not put the value 2 here on the root. That is because this sign on its own, without any number here, already means square root. Okay? So if you now write this, you now put 2 here and call this a square root, this would be mathematically not correct. So if you have a 2 here, all you simply write is the square root sign. And you don't put any number here anymore. So if you have from 3, 4 upwards, anything that's bigger than 2, you put the root sign here. So this simply means the square root of x. So x raised to the power 1 over 2 simply means the square root of x. Take for example, if you ask to simplify, say 4 raised to the power 1 over 2. Clearly, the power here is a fraction. So we must apply the fractional index law here, or the fractional power law here. So this gives us the denominator is 2. So that is, we have our square root sign here. So we should have put 2 here. But since this sign already stands for square root, we can't put 2 here anymore. So that becomes the square root of 4. would have raised it to power 1. But then, when you raise it to power 1, it doesn't change the number. So the square root of 4 simply means what number can multiply itself, 2 times. Square root is 2 to give you 4. The number is 2. Since 2 times 2 is 4. Therefore, the square root of 4 is 2. And I've applied the fractional power or root law. Law number 7, which I shall call the same power law. Very simple. What this law is saying is that if in our bracket we have more than one base, for example, we have x and y, and these two bases are both raised to a particular power outside, let's say power n. So this is x, y, all raised to the power of what? N. So here the bases are x and y, multiplied together, and it's a common power outside. What this law is saying is that same power law means x and y have same power outside. By this law, what we simply do is this. The first base is x, so x will go with power n. So we write x raised to power n times y will also go with power n. We write y raised to power n. So we can simply write this as x raised to power n, y raised to power n, since these two mean the same. So we can take out this multiplication sign and just write x raised to power n, y raised to power n, with the understanding that these two mean one and the same. This also applies in a case of division. For example, if what we had here was x divided by y all raised to power n, the same thing. So we can split this up. So the numerator is x, it will take power n, divided by the denominator is y, it will also take what? Power n. So these two things are one and the same. For example, if you have in a bracket 2x raised to power 2, what do you see here? Inside the bracket there are two bases. The first base is 2, second base is x, and both of them are raised to a particular power outside, which is 2. So by the same power law of indices, that means the first base 2 here will go with the power outside 2 times the second base is x, it will also go with power 2. So that 2 raised to power 2 means 2 times 2, which is what? 4 times x squared. Since we can write this without the multiplication sign, this simply means 4x squared, or 4x raised to power 2. In this same power law, we should observe that here the power of x is 1 and the power of y inside is 1. But it's not always 1. Sometimes the power of x and y are other numbers apart from 1. And let me show you what happens. So if we have, say, x raised to power a, y raised to power b, or raised to power n. This is also the case of same power law. But here, the power of x is no longer 1, but it's a. So a could mean something else apart from 1. B means something else apart from 1. The same power law still applies, exactly. So the first index form here is x raised to power a. The second one here is y raised to power what? B. So by the index power law, by the same power law, we distribute this power outside, to each of the bases or each of the index forms inside. So the first one is x raised to power a. So we have x raised to power a. That index form will go with the power outside, which is raised to power n. Times, we now write y raised to power b. The power outside will also go with it, raised to power what? N. But we know already that if we have two powers, outside, what do? We multiply out the powers. So this simply means we can write this as x raised to power a times n is an times b times n is what? Bn or nb. Since we can write this without this sign, we can simply write this as x raised to power an, y raised to power what? Bn. We've applied the same power law. This law also applies if we are dividing. X raised to power a, for example, divided by y raised to power b, or raised to power n. We can still split this into x raised to power a, and then the power outside will follow, divide by y raised to power b, and the power outside will also follow. So this will give us x raised to power a times n is an, divided by b times n is y raised to power what? Bn. So we've applied same power law in both cases. Now we shall present few examples so that we see how we apply most of these laws in simplifying and solving certain problems. Example: simplify the fifth root of 36 raised to the power 2.5. Now to simplify this problem, and every other one that we shall encounter in future. All we have to do is to apply the laws of indices. In some problems, you can apply 2 laws. In other problems, 1 law. In other problems, as many as 3 to 5 laws of indices. So our job is to apply the laws of indices and try to make this expression as simple, as possible. So we have the 5th root of 36 raised to the power 2.5. The first law that comes to my mind here is that of the fractional index law or fractional power law, which says that x raised to the power particular power a over b can be written as the bit root of what? X raised to the power a, or the bit root of x raised to the power a. This comes to my mind. So I look at this as this. So where I have b here, I have 5. Okay? And where I have a here, I have 2.5. So if we apply the fractional power law of indices, because take note, in this law of indices, we can also write these laws from right to left. That is to say that I can write the bit root of x all raised to the power a as x raised to the power a over b, or the bit root of x raised to the power a inside as x raised to the power a over b. So going by this law of indices, I can write this expression as the base is 36. Okay, what's my a? My a is 2.5 and my b is what? 5. So a over b. That becomes raised to the power 2.5 divided by what? By 5. So I want to make it simple. I got this 2.5. I want to now write it as 36 raised to the power 2.5, and I take the 1 over 5 outside the bracket. The same thing, because there's a law that tells me that if I have 2 powers, one inside and the other one outside, the law says I can multiply both powers. So my first power is 2.5, the other one is 1 over 5, so that 2.5 times 1 is 2.5 divided by 5. So these two things mean the same. And I'll go ahead and say, okay, I want to change this 2.5 to something else. Now I know that if I divide 5 by 2, 5 divided by 2, this will give me 2 and 1 over 2, which is the same thing as what? 2.5. So there's a fraction that gives birth to this decimal. I want to avoid using this decimal as much as possible. So there's a fraction that gives birth to 2.5. And what fraction is that? 5 over 2. So I want to rewrite this again as 36 raised to the power 5 over 2. Then the power outside is 1 over 5. This way, I've gotten rid of the decimal and I now have fractions to deal with, because I want the powers to all be fractional powers. Now, the power inside is 5 over 2 and the one outside is 1 over 5. By the fractional power law, I can now multiply both powers, and that will give me 36 raised to the power 5 over 2 times 1 over 5. So that 5 can cancel 5, and what I have left is 36 raised to the power 1 divided by 2, 36. And by the fractional power law again, I have 36 raised to the power half, and this simply means the square root of 36 raised to the power 1, which is the same thing. So the square of 36 means what? The number that can multiply itself 2 times to get 36. What number is that? Is 6, because 6 times 6 is 36. Therefore, 6 is a square root. Therefore, the square root of 36 is 6. And by so doing, this expression that looked like this, the 5th root of 36 raised to the power 2.5, has been simplified to just what? To 6. So what you see here and 6 are just equivalent. Another example, we're asked to simplify 10x raised to the power 5 times 4x raised to the power 3, all of it divided by 8x raised to the power minus 2 or negative 2. So I have here 10x raised to the power 5 times 4x raised to the power 3, all divided by 8x raised to the power minus what? 2. We want to simplify. That means we want to have a very simple version of this expression. And the only way we can do that is by applying 1 or 2, or a few laws of indices. So I see one thing on the numerator. I've seen multiplication here. So what comes to my mind first is the first law of indices that states that is called the multiplication law of indices. The law tells us that what? It tells us that if I have 2 index forms, x raised to the power a, I have x raised to the power b, that as far as the 2 index forms have the same base, that law says I should take one base and then add up the exponent or add the powers up. So I find that here also. I see x raised to the power 5 here, I see x raised to the power 3 here. They both have the same form, the same base. But I see 10 here, I see 4. They're not the same. Since 10 and 4 here, the coefficient of these 2 index forms are not the same, I can multiply them out. So I can multiply 10 times 4. Then I will now apply the first law of indices on these two index forms, x raised to the power 5 and x raised to the power 3, since they are of this form. So since they have the same base, by the first law of indices, I can take the base out, one base out. So that's x raised, let me just say times x raised to the power 5 plus what? Plus 3. The first power is 5, the second power is 3. I add. All of it divided by x raised to the power 8x raised to the power minus what? 2. So the numerator again, I'm still there. So 10 times 4 gives us 40 times x raised to the power 5 plus 3 gives us 8, divided by 8x raised to the power minus 2. I now say something. Of course, 40 times x raised to the power 8 is the same thing as 40x raised to the power 8, divided by 8x raised to the power minus what? 2. Another law comes to my mind at this point because I'm now dividing. So the division law, which is law number 2 of indices we have discussed already, comes to my mind. That if I am dividing two index forms that have the same base, the law says that I should do what? I should take the base that have the same. I should take the base and subtract the exponent or subtract the powers. So I can apply that on x raised to the power 8 and x raised to the power minus what? 2. However, 40 and 8 are different, so I can divide them. So I can simply write this as 40 divided by 8, and I apply the second law of indices on these two guys. So since I have the same base here, I can take one of the bases, x, and then the power here is 8 minus, the power here is minus 2, minus what? 2. So this will give us 40 divided by 8 is 5x, 8 minus times minus is plus 2. So that 8 plus 2 is 10. And I have 5x raised to the power 10. And we have simplified the expression. 10x raised to the power 5 times the whole of this has been simplified to what? 5x raised to the power 10. Our final example on indices here is we want to simplify this expression. The cube root of x raised to the power 9, y raised to the power 1 over 3, z raised to the power half times y raised to the power 8 over 9 times in bracket 3 raised to the power 6, x raised to the power 6, y squared, z raised to the power 1 over 3, and we have the power outside minus 1 over 2. The first thing I would like to do here is to change this cube root sign. And I know from my laws of indices that the cube root of what I have here can be written as what? As x raised to the power 9, y raised to the power 1 over 3, z raised to the power 1 over 2, all of them raised to the power 1 over 3. Because this simply means the cube root of what I have in bracket. So times y raised to the power 8 over 9 times, now I come over here, there's a power outside and I have different index forms inside the bracket, and there's a law that says that once I have a power outside and I have more than one index form, that I should distribute the power outside to each of the index forms. So I'll distribute. The first one is 3 raised to the power 6. I'll give it the power minus 1 over 2 times the second one is x raised to the power 6. I give it the power minus 1 over 2. The third one is y squared. I give it the power also minus 1 over 2. The last one is z raised to the power 1 over 3. I also give it the power minus 1 over 2. Now you can decide to approach this problem, in a different way from this. Because if you look at this, last time, you observe that the power here is negative. So you may choose to start this problem, by applying the negative power law here, and there'll be no problem. As long as you are using the correct laws, applying the correct laws of indices, in the end you're going to have, nearly the same expression, if not exactly the same. So I choose to apply the, this law of indices that says that once I have a power outside and I have, more than one term in my bracket, I should distribute the powers across. I choose to use this one first. So, and I can still apply that same law to the first bracket, because here I have a power 1 over 3 outside and I have more than one index form inside. I distribute. So the first one is x raised to the power 9. We'll go with the power 1 over 3 times y raised to the power 1 over 3. We'll go with the power 1 over 3 times z raised to the power 1 over 2. We'll go with the power 1 over 3 times y raised to the power 8 over 9 times, here I have 3 raised to the power 6, I just write it down, minus 1 over 2 times x raised to the power 6 minus 1 over 2 times y squared 1 over 2 times finally z 1 over 3 minus 1 over 2 outside. And I want to simplify. So There are law that tells us that what? If we have two powers, one power inside and the other one outside the bracket, what should we do? We should multiply out the powers. So I'll multiply the power inside the bracket and the powers outside the bracket. So the first one I have here, x raised to the power, 9 times 1 is 9. Then 9 over 3 is 3. So that's x raised to the power 3. Times second one is y. 1 times 1 is 1. 3 times 3 is 9. So that is 1 over 9. Times the third one is z. 1 times 1 is 1. 2 times 3 is 6. So 1 over 6. Times the next term, y raised to the power 8 over 9. Times this one, 3 raised to the power 6 times minus 1 is minus 6. Minus 6 divided 2 is minus 3. Times x. The same thing here. 6 times minus 1 is minus 6. Divided by 2 is minus 3. Times y. 2 times minus 1 is minus 2. Minus 2 divided by 2 is minus 1. Times z. 1 over 3 times minus 1 over 2. 1 times minus 1 is minus 1. 3 times 2 is 6. So minus 1 over 6. And I have the simplified version from my original problem. Very good. You see, it's getting simplified. So all I see here is multiplication everywhere. So what comes to my mind? The first law of indices, which is what? The multiplication law of indices. So I start with the first base, which is x. And now check. I have x here. Another x somewhere? Yes. Another x is here. And since I'm multiplying, I can apply the first law of indices. So by that law, I'll take the base out and I add up the powers. So the power here is 3 plus the other power is minus 3. So plus minus 3. Times the next base I have there is y. And I'll check, is there another y somewhere? Yes, there's a y here. Another y? Yes, another y is here. So they all have the same base, so I'll add the exponent. So I have y into the first power here is 1 over 9 plus the second power here is 8 over 9 plus the third power here is minus 1 plus minus 1 times the next one I see there is z. Another z, yeah, check, there's another z here. So I add their powers. So I have here z, the power here is 1 over 6 plus the power here is minus 1 over 6 times another one. Yes, there's one term that is left. That is times 3 raised to the power negative 3. So I proceed. This will give us x raised to the power 3 plus minus 3 is 3 minus 3 times y. I have here 1 over 9 plus 8 over 9. This is simply 1 over 9 plus 8 over 9 plus times minus is minus 1 times z into 1 over 6 plus times minus is minus 1 over 6 times, I want to leave it like this for now, 3 raised to the power minus 3. I want to simplify further. So this is x raised to the power 3 minus 3 is 0 times y. Now these are fractions. Now the LCM here of the LCM here is 9, and when you tidy this up, what we have here is 0 times z. 1 over 6 minus 1 over 6 again is 0 times, I have here 3 raised to the power minus 3. So there's a law of indices that tells us that any number raised to the power 0 is 1. So x raised to the power 0 is 1 times y raised to the power 0 is 1 times 0 raised to the power 0 is 1. Then times what? I have here 3 raised to the power minus 3. So if I multiply out all these terms, 1 times 1 times 1 times this is nothing but what? 3 raised to the power minus 3. I can leave it here if I like, but since I now know my laws of indices, I want to take one step further. Now this is the case of negative power law, because I have the base is 3 and the power is minus 3. So by the negative power law, I can write this as 1 all over 3 raised to the power 3. And of course, 3 raised to the power 3 means 3 times 3 times 3. And that is equal to 1 all over what? 27. So you can imagine that the whole of this bunch that we were given has been simplified to what? 1 divided by what? 27. And this is a simplified form of this. We now look into the theory of logarithms. And we shall see here that logarithms and indices are closely related. As a matter of fact, that almost the same thing. So as a way of definition, the logarithm of a number to a given base is the value of the power to which the base must be raised to produce the number. Now let me try to make you understand this definition of logarithms. Very simple. Now, if you are asked now, what is the logarithm of 8 in base 2? Now we shall write this, in short form as the log. We write 8, we write 2 down. So this simply means the logarithm of 8 in base 2. So the question now is this: what is the logarithm of 8 in base 2? So when you ask to find the logarithm of 8 in base 2, what are you expected to do? Or what is expected of us? Very simple. Now, by this definition, we are simply saying that the logarithm of 8, this 2 here is called the base. The logarithm of 8 in base 2 simply means the number which you don't know, or whatever number it is, such that when you raise 2 to that particular power, you get 8. That's that simple. In this example, you see that if you raise 2 to power 3, what do you get? You get 8. So this base here is 2. And if you put 2 to the power of 3, you get 8. Since that happens, it follows that, or it means that the log, or the logarithm of 8 in base 2 is nothing but what? It's nothing but 3. Since 3 is that power that you can raise 2 to get 8. So the log of 8 in base 2 is 3. So you can change this log to an index form, and from index form back to log. And they both have something in common. To write this number in index form, you see that the base here is 2, and in index form the base remains what? 2. Then 3 here will come up, because 2 to the power 3 is 8, equal to 8. So this number in log form is the same number here in index form. In log form the base is 2, in index form the base is still 2. Then in log form, the 3 you have here at the right hand side becomes the power of 2. So that 2 to the power 3 is 8. So in log form, you simply say that the logarithm of 8, the log of 8 in the same base in base 2 is 3. Because when you raise 2 to the power of 3, you get 8. Another example, if you are asked for the logarithm of 81 in base 3, what will it be? Very simple. You look for a number such that 3 raised to that particular power gives us 81. What number is that? Let us see. 3 raised to the power 1 is 3, not 81. So the log of 81 base 3 cannot be 3. Let's see another one. 3 raised to the power 2 is 9, and 9 is not 81. So the log of 81 base 3 cannot be 9, and cannot be 2 rather. Again, 3 raised to the power 3 is 27, and 27 is not 81. So the log of 81 base 3 cannot be 3. But 3 raised to the power 4 is 81. Therefore, we have raised this base 3 to the power of 4. So that power here, 4, becomes the logarithm of 81 in base 3. So since 3 raised to the power 4 is 81, it follows from here that the logarithm of that 81 in the same base 3 is equal to 4. So these two numbers are the same, they're equivalent. But here, the number is in a log form, while over here, the number is in the index form. One last example. If you're asked to find the logarithm of 25 in base 5, what would it be? You can pause the video and find out what it should be. Very simple. You check, what number will I raise 5 to get 25? That simply means 5 raised to the power what is 25. Once you figure out the number, then that becomes the log of 25 in base 5. So 5 raised to the power 1 is 5, and that is not 25. So the log of 25 base 5 cannot be 1. And I'm trying another number, 5 raised to the power 2, whoops, is 25. Since I have 25 here, it therefore means that I have to raise 5 here, this base, to the power of 2 to get 25. Since that has happened, it simply means that the logarithm of 25 base 5 is 2. So 5 raised to the power 2 is 25. How do you now write this in log form? Remember, the log and the index form both have the same base. The base here is 5. So in the log form, the base remains 5, base 5. Then 25 here equal to 2. So the log of 25 base 5 is 2. So if you have a log form, for example, the logarithm of, let's say, 4 base 2, I say is equal to a number x which you don't know. How do you change this to index form? Very simple. The base here will just take this guy on his head. So that becomes, so in index form, this becomes 2 raised to the power x equal to 4. And what you have here is a log form, and what you have here is equivalent of this, but now in the index form. One last one. If you have the logarithm of, let's say, 10 to base 3 equal to some number, let's just say some number y, we don't know what it is, and you're asked to write this log in the index form, what do you do? Very simple. The base here, 3, will take this guy y on his head. So you simply write 3 will now take y on his head, y equal to 10. So in index form, log 10 base 3 equal to y simply means 3 to the power y equal to 10. So I guess with these illustrations now, you understand what we mean by the logarithm of a particular number. So you're asked to find the logarithm, of say 50 in base 3. What does it mean? You should look for a number that when you raise 3 to, you get 50. And if that number can be found, then the logarithm of 50 base 3 has been found. Common logarithms. Now we could have logarithms in different bases. Okay, for example, log 8, this is in base 2. For example, log 10, this is in base 3, of course, and so on and so forth. However, there's a particular base that is called a common logarithm, and that is base 10. So if you have the log of a number, say the log of some number n, and the base here is 10, then this is called a common logarithm. So the log of a number to base 10 is called a common log. Now, oftentimes, if a log is a common log, that is to say, if a log is in base 10, instead of writing log n base 10, we simply write log n without the base. So when you see a log of a number written without a particular base, what that should tell you is that that particular log is a common log. Common log in the sense that the base of that logarithm is 10. For example, if you see us write, or if we write the logarithm of 3, there is no base there. This simply implies that this log is a common log. So this log would have been written as the logarithm of 3 in base 10. So these two things mean one and the same. So log 3 base 10 is a common log, which is written as log 3. So going forward, if you see log 3, write log 3 base 10. If you see log 3 base 10, you write log 3. However, there is no crime whatsoever if you choose to write log 3 base 10 instead of log 3 only. But have the understanding that whenever you see your log without a base, that automatically means that the base you're working with is already in base 10. So log 2 will mean what? Will mean log 2 in base 10. And we call this the common logarithm. Just as we had in the case of indices, we also have laws of logarithms. So we shall take the following laws. So L1 is for law number 1. And this law is called the addition. Sometimes you can call it the product law. Addition product law of logarithms. It states the following. That the logarithm of a number, say m, in a particular base a, plus the logarithm of a number, say n, in the same base a, is equal to the log of m times n in base a. What this is saying is very, very simple. That the sum of the logs of two numbers is equal to the log of their product. But take note, this only happens when both logs you have here have the same base a and base a. So if the first log here is, let's say, base 2 and the second log is base 4, you can't apply this law. So both logs must be of the same base. And of course, most important, another point is that both logs must have coefficient of 1 at this point. So if here is anything other than 1, you can't apply the law directly like this. So you can only apply this law like this if this point here is 1 and the both logs have equal base. For instance, if you have the logarithm of 3 base 2 plus the logarithm of 5 in base 2, we can apply the addition law here. So since my log here has base 2, the second log here has base 2, and between them I am adding, and the coefficient of this first log is 1, this other one too is 1. So I can write this logarithm as 1. This becomes the logarithm, the base is 2, of what? 3 times 5. So this becomes the log in base 2, 3 times 5 is 15. So that log 3 base 2 plus log 5 base 2 now becomes log 15 base 2. We've applied the first law of logarithms called the addition or the product law. Law number 2, subtraction quotient law. The law says that if I have the logarithm of m again in base a, now minus the logarithm of n in base a. That this should be the same thing as the logarithm in base a of m divided by n. So we are saying here that the difference of the log of two numbers in the same base is equal to the log of their quotient. Again, the same rules will apply here. Number one, both logs must be of the same base, base a and base a. And again, the coefficient of this log here must be 1, and this one here also must be what? 1 here. So if that happens, we can apply law number 2. For instance, if we have, say, log 3 base 2 minus log 5 also in base 2, we can apply this law. Since both logs have the same base 2 and they both have coefficient of what? 1. So this becomes the log, I'll take 2 base 2 into, here is 3 divided by what? By 5. So log 3 base 2 minus log 5 base 2 is the same thing as the logarithm of 3 over 5 in base 2. The third law is a power law, and I have two parts for it. So the part A of it says that the logarithm of m raised to power n in base a. What is happening here? I have a log m, and that log is raised to a particular power. Say the power is n, and there's a base a. That I can write this as this. So if we have something like this, I can transfer this power down here and write n times log m in base a. So you have a particular log, and that log is raised to some power. You can transfer the power to the left side of the log and write n times log m in base a. Very quick example, for instance, if I have say the logarithm of say 9 in base 2. Of course, it doesn't look like this initially, but I know that I can write 9 as 3 raised to the power 2. Are we there? Good. So that this now has this form. So now if you compare what you have here with this law, you see your n is like 2. So by this law of power, I can transfer 2 to the left, and I can now write this as 2 times the log of 3 in base 2. Part B of it says that the log of m base b raised to the power n is equal to, now here what do you observe? In the part A of the law, you see that it is a log itself, log m, that was raised to the power n. But in part B of it, it is the base b that has a power. So note the difference. Here the base has a power, while here in part A, the log itself has a power. So here the base is b raised to the power n. So when we have this, we simply write this as, this power of the base is n, we write 1 divided by n, close the bracket, log of what? M base b. So log of m base b raised to the power n is equal to 1 over n times the log of m base b. For instance, if you have the log of 9 base 3 raised to the power 2, so the power here is on the base. This simply means 1 over 2 times the logarithm of 9 in base 3. So we call this the power law. The next one is logarithm to the same base. So if we have log m and the base is also m, the logarithm of the number and this base are the same. This is equal to 1. That's all. So we say that log to the same base is 1. For instance, the logarithm of 3 in the same base 3 is 1. The logarithm of 8 in the same base 8 is 1. And that's it. Law number 5, which we call change of base. Now, sometimes you have a problem, okay, to solve or to simplify, and the problem has different bases. So one thing you can do is to change the problem to a certain base of your choice. What I mean is this. Let's take this law first. Now, if we have the log of, say, m in base n, so this is the log of m in base n. If for some reason you are not comfortable with this base and you need to work in a particular base you are either familiar with, okay, for instance, if you want to work in a common base or a common logarithm rather, and what is that? That is log in base 10. So what do? You can convert this logarithm that is formerly in base n to a logarithm in base 10, which is called a common logarithm. So what do? This simply will be the logarithm of m, the number m, in the new base of your choice, which is what? Now is 10. Divided by the logarithm of this base now becomes the log of n in your new base 10. So this just becomes log m over log n, since the common logarithm can be written as this. So if you choose to convert this log to a log in base 2, what would it be? It will simply be the log of m in your new base 2 divided by the log of n, this n now, in your new base 2. These two things you see here are the same. So the log of m base n is the same as the log of m in base 2 divided by the log of n in base 2. So you can change base from one base to any other base of your choice. For example, if you have the log of 5 in base 2 and you're asked to write this log as a log in base 3, which means you must change your base from 2 to 3. So that will simply be the log of 5 in your new base 3 divided by the log of 2 in your new base 3. And what you have here on the left hand side are the same. So log 5 base 2 is the same as log 5 base 3 over log 2 base 3. We shall now take some examples to illustrate what is happening here. Example, simplify the log of root 2 base 7 plus the log of root 18 base 7. So we're going to apply the laws. So there's a law I'm seeing here already. This is the addition, the sum of two logarithms. So what comes to my mind is the first law of logarithm, which is what? The addition product law. So you should recall that we know already that the logarithm, right, of m in base a plus the logarithm of n in base a is what? The logarithm of what? The product mn in base a. So I see that here. So I want to write the log of root 2 base 7 plus the log of root 18 base 7 as the logarithm in base 7 of root 2 times root 18 by the first law of logarithms which we have already learned. So this becomes the logarithm in base 7 of, now root 2 times root 2 is what? Root 2 times is root 2 times 18 by our sorts. That gives us the logarithm in base 7 of root what? 2 times 18 is 36. And the square of 36 is 6. So that is nothing but the logarithm of 6 in base 7. So log root 2 base 7 plus log root 18 base 7 is nothing but what? Log 6 base 7. Example. Simplify log 27 raised to the power 3 over 4 in base 4 plus log 9 raised to the power 3 over 2 in base 4 minus log 81 in base 4. Now the log we have in this problem is that the three terms are all in the same base 4. Now if the bases were different, what would have done would have been to convert the three problems to a common base and then would have applied the change of base technique. However, I've seen clearly here that the first two logarithms have addition between them, so I can apply the addition product law, and here I have subtraction. I can apply the second law, which is the subtraction quotient law. However, I'll take them one at a time. So I can apply the first law of indices of logarithm rather on these first two terms, and now that becomes the log in base 4 of, so log m base a plus log n base a is what? Log m times n in base a. Good. So here our m is the whole of this number, so that is 27 raised to the power 3 over 4 times our n is the whole of this number, 9 raised to the power 3 over 2 minus log 81 base 4. We can't involve this because here is minus, and the law only says that if we have plus in between them, then it's applied. So we apply to the first two terms, leaving this one for now. So if we pick what we have inside this bracket to deal with, we'll have the following. Now we should apply indices here. However, we have a little problem here. Now here the base is 27, while over here the base is 9. So we can't apply the first law of indices. However, if we do a little simplification here, it can be applied. How? I can write 27 as 3 raised to the power 3. I can write 9 also as 3 raised to the power 2. If I do that, then both terms will have a common base, and I can apply my law of indices. as follows. So I can write this now as the logarithm in base 4 of 27 is the same thing as 3 raised to the power 3, right? 3 raised to the power 3, and what is outside? 3 over 4. Times, I can write 9 as 3 raised to the power 2, and then the power outside is 3 over 2, minus the log of 81 in base 4. So this gives us the log in base 4 of, I have two powers. Remember your power law of indices. This is 3 raised to the power 3 times 3 is 9 over 4 times 3. There are two powers again here, 3 and 3 over 2. In fact, 2 will knock off 2, and what is left there is 3, minus the log of 81 in base 4. So I can now apply the law of indices, to these terms in the bracket. So this will give us the log in base 4, remember, of, now I have the bases are the same, so I will pick the base, 1 base 3, I add the exponent, so 9 over 4 plus 3, minus the log of 81 in base 4. So this is equal to the log in base 4, 3, this is 9 over 4 plus 3, the LCM there is 4, if you tidy that up, you get 21 divided by 4, minus the logarithm of 81 in base 4. Now at this point, I can now apply law number 2, because I have log in base 4, I have log in base 4, and between them I have subtraction. And the coefficient here, I have here 1, I have here 2, 1, or minus 1 if you like. So I can apply law number 2 here of logarithms that says what? That this log is simply equal to what? The quotient of the individual logs. So I can now write this as the logarithm, I take 4 out, into my m is like, so this is like my m, and my n is 81, into 3 raised to the power 21 over 4 divided by 81. So once again, I see something here very quickly that I can apply my indices here, because I can express 81 to have the same base as the numerator, because 3 raised to the power 4 is 81. So I can write this as the logarithm to base 4 of 3 raised to the power 21 over 4 divided by 3 raised to the power 4. Since 3 raised to the power 4 is 81. Now, the bases are the same. I can now subtract the exponents. So by indices, I can write this as the log in base 4 of, I take 1 base, I have 21 over 4 minus the second power, which is what? 4. So you have to tidy this up. The LCM here is 4. And if you tidy that up, you're going to get the log in base 4 of 3 raised to the power 5 over 4. So what I have here is now the log to base 4 of 3 raised to the power 5 over 4. And something comes to my mind again, the power law of logarithms, that tells me that if my log has a power, that I can bring the power down to this other side. So this, if I apply that, this becomes, I bring 5 divided by 4 down, get the logarithm of 3 in base 4. And that will be a simplified version of this logarithm. Let us now take a last example for the part 1 of this lesson. Given that log 2 base 10, which is a common log, is equal to 0.3010, and log 5 base 10, a common log again, is equal to 0.6990. We are asked to evaluate the logarithm of 25 in base 2. So, what do we see here? We should observe something. We observe that what we are given is in base 10, which is called a common logarithm, and what we are asked to evaluate is in base 2. Therefore, we are working with two different bases, and this will pose a problem to us. So what we do is we apply a change of base to see that we work in the same base. Since we are given logs in base 10, it's advisable to convert the log we want to evaluate from base 2 to base 10. So to do that, we simply apply the change of base formula. So log 25 base 2 to base 10 becomes log 25 base 10 divided by log 2 in base 10. The next thing we're going to do now is, our problem is now in log 10, in base 10 rather, just like what we are given here in base 10. The next thing we want to do is, we are given log 2 and log 5. So our next step is to break 25 in terms of the given logs. Thank God, in the denominator we already have log 2, which is okay. The next thing is to break 25 down, because we are not given log 25 in the problem. We are given log 2 and log 5. So we must break down 25 in such a way that we can have log 5 and log 2. So I'll write this as the logarithm in base 10 now. What is 5? 25. 25 is simply 5 squared divided by the log of 2 in base 10. Now remember again, by my power law of logarithms, I can send this guy to the left. So if I apply that law, I can simply write this as 2, the log of 5 in base 10, divided by the log of 2 in base 10. I was given log 2 and log 5 as these values respectively. So I can now put these values in, and I will now get 2 times, what is log 5? Log 5 is 0.6990 divided by log 2. What is log 2? 0.3010. If I multiply out, I'm going to have 1.398. 2 times this divided by 0.3010. So this gives us 4.645 approximately. Therefore, the logarithm of 25 in base 5 is equal to 4.645. So the trick in this question was that we had to convert what we are looking for to the base, to have common base as what we are given. Log 2 is in base 10, log 5 is in base 10, or common log, and we asked to evaluate a number in base 2. So we converted a number to a number in base 10, just like what we are given to solve. Please don't forget to leave a comment on this video. Also like and share with your friends. And please subscribe to this channel if you've not done so already. Thank you, and see you in the part 2 of this lesson. Bye-bye.